Hello everyone and welcome to another video of myself looking at websites from technology companies in the quantum technology space. In today's video we are going to take a look at Quantum Motion, and with that let's take a look right away at their website. So this is what it looks like. We see a very cool animation going on here with those very abstracted elements here. So looks like some circuits, then now it looks like some traffic going on here. There's like a city. Okay, with that let's scroll down a little bit and see what they are actually doing. And the easy thing for me is I just have to read it because here it says what we do. Quantum Motion is developing a revolutionary technology platform, not just a qubit, but a scalable array of qubits based on the ubiquitous silicon technology already used in smartphones and computers. Our team of quantum engineers are developing quantum computing architectures that are compatible with standard silicon processing, unlocking the power of quantum computing with the simplicity of silicon. By creating a scalable quantum computing technology, we will be able to tackle current intractable problems in fields as diverse as chemistry, medicine, and artificial intelligence. Okay, then there are some news here. So Quantum Motion appoints president and COO to lead company extensions and commercialization, and so on. Here it says our solution, silicon-based integrated circuit technology, is the bedrock of the digital revolution. It allows billions of transistors to fit in the size of a stamp, unlocking the power of quantum computing with the simplicity of silicon. Even a single logical qubit might require 1,000 physical qubits to allow the robust error checking required for dependable calculation. Only by using a scalable qubit technology can we keep the chip the size of a stamp and not a stadium. A smartphone based on vacuum tubes rather than silicon integrated circuits would be 10 centimeters thick and cover an area the size of inner London. The same scaling arguments are important for quantum devices. We need an ultra scalable architecture for quantum computers to reach their full potential. So the argument is that, okay, we have this silicon technology stack already, right? Like Moore's law, we've been working on this since forever, or not myself, but like engineers, like silicon engineers have been figuring out how to miniaturize these transistor elements, which are at the very core of our today's technology since a long time. And there is this famous law called Moore's law, which comes, I think, from the former Intel CEO, which basically says within a given amount of time, the size of these transistor elements is always halving. So by that you can basically say if you keep the chip size constant, with every of these periods in time, you will get double of the compute power at the same size of the chip, which is basically the same price, right? And now what they say, what Quantum Motion is saying, let's use this existing technology stack, let's use the silicon technology to create quantum systems, qubits with that, because what we need is, we need something that is small enough such that like we don't have to create these huge compute centers, these huge compute systems. We have to keep it small. And this is referring also to other systems, like if you, for example, look at ion systems, you always need lasers around it. So you need a large peripheral of lasers to actually, let's say, manipulate those tiny ions, which actually also reside on the chip. When you then, for example, look at the superconductors, you always need waveguides and like long attenuators and stuff on the chip, which also makes it quite big. And their basic proposal is, okay, let's use the silicon, the existing technology to build those systems. And then they also make this comparison here with silicon versus vacuum tubes. So before the transistor was built in these solid state systems, so before we used silicon, there was already something like a transistor, which was basically a tube. And you might remember that from like these old vacuum tubes on the amplifiers, like music amplifiers, for example. It's the same principle, like you also use more or less a transistor, but it's basically created in a different way. It's using vacuum tubes and a different mechanic in order to create that, which is much bulkier, right? Because you need all of these glass components, and inside you need the metal components, and then you need to make sure that the electrons are flowing in there. So it's much more difficult to realize. The other one is also difficult. Silicon is not easy to manufacture at these very small sizes, but it's much tinier, much smaller now. And that's the proposal that quantum motion is actually taking as a basis for, I guess, their technology stack, which we will learn about in a second. From an investor's point of view, we see Bosch, we see Porsche, but we also see other people here, like other groups like Parkwalk investing in innovation. So there are different institutions and companies investing into this quantum motion company. And then, you can also get in touch with them. Leave your name down here. Okay. With that, let's also look at the About page and see what else we can find out. So About, the ultimate upgrade. Chips similar to those in a phone will perform true quantum computing. I guess now we will learn something about the technology. And just as a side note, I'm maybe also a bit biased because I've also worked once in the lab where we were trying to use silicon, so CMOS technology, which is the standard technology that our silicon systems are based on today. They were also using these technologies to create so-called spin qubits. So in case we don't find anything here, I might also mention a couple of words about that. Okay, it says the most powerful computer on the planet hasn't yet been built, but we have the blueprint for putting it together. At Quantum Motion, we combine deep expertise in fault-tolerant quantum architectures with the hardware knowledge to realize qubits in silicon. The development of a fault-tolerant quantum processor will open possibilities far beyond the reach of today's small quantum computers, and even the emerging noisy quantum intermediate scale, the emerging noisy intermediate scale quantum processors, so NISQs. This technology will power high-impact applications in areas vital for human progress in the 21st century. In software discovery for new chemicals, materials, and drugs, the reduction of wastage through optimization of resource usage, and enabling new models for AI and machine learning. Our goal is to fast-track the development of true fault-tolerant quantum computers and reach 1 million qubits and beyond by leveraging existing knowledge in device fabrication within the trillion-dollar silicon industry. It is predicted that by 2025 there will be more silicon transistors on the planet Earth than human cells. Creating qubits using conventional transistor process technology will be revolutionary in its democratizing impact on the power of quantum computers. At Quantum Motion, we are marrying 50 years of global CMOS development with world-leading expertise in quantum design and architectures. Our team is transitioning this work away from theoretical research in universities to realize these designs in real-world quantum manufacturable processes. And then here we see the whole team of the different experts that we read about before. So it's quite a bit large team of people that are already working on this from various different areas. We see they have, I guess, here London, Oxford, and Sydney as their locations, and then again you can get in touch with them here. And then there is also like a news tab. There is something about the careers, and then you can contact them. So there is not, let's say, too much details about the technology itself yet, right? I can also say that, like on the news tab, I'm recording this in June 2025, so there is not, let's say, much super new here yet, because the last one is, I think, from April. Let me quickly maybe also say a couple of words on this silicon-based or CMOS-based chip related stuff. So at least if I could make a guess, I would guess that this is also relating to spin qubit systems. So basically, you're trying to take single electrons within a silicon system, embedded within silicon, and then you basically use their spin state, so spin up or spin down, as a two-level system for your quantum computer. And you need to do a lot of things to actually create such a system where you have like a single confined electron spin, which you can flip up or down to make those manipulations. But if you can actually get this up and running, you can shrink it down, or you have to actually shrink it down if you want to do it in silicon, to like very small scales of nanometers. So really use like latest state-of-the-art cutting edge technology, and then you can really like shrink it down and use those electron spins. And I mean, if you would like me to actually do a video on this specific technology and how it works and like how you create a two-level system and what you have to do, then please let me know down in the comments below. I'm happy to make a video about that as well. And I hope you liked this very short introduction about quantum motion. Please make sure to always stay hydrated, and see you in the next one. Bye bye.